Okay, so welcome to today's QuSCo on Air lecture. We are a small group here in Munich, but actually 3 QuSCo students here. So Amit, Marwa, and Alistair, Marshall. And so we'll talk about cooperative pulses today. So that was requested, and I'm of course happy for this request, and I'm happy to give you a little bit of a summary or the key ideas of these cooperative pulses. So actually I start out with just an example of a quite complicated pulse sequence. That's a typical NMR pulse sequence when you study complicated proteins. But it could equally be like a sensing experiment or a quantum information processing experiment, creating some quantum gates. So typically we have a lot of pulses that we apply during our experiments. And the question is, how can we make them robust? How can we make them as fast as possible? So in general, when we optimize pulses like this, we have multiple objectives, and this is already an oversimplified picture. So on the one hand, we have the fidelity that we want to optimize. We want to optimize the robustness of the pulse sequence with respect to
Stefan, sorry to interrupt you.
Yes. Yes.
We can't see the screen, so the screen is not shared.
Oh, okay. Just a second. Is it?
Okay.
Do you see it?
Yep.
Okay, great. Actually, I'm not sure if I can go. Well, maybe I just leave it in this mode, then we see the next slides also. That's okay. Okay, so basically we have. And is the sound okay? Can you hear me okay?
Yes, loud and clear.
Okay, good. So we have several objectives that we usually would like to optimize. And for example, we also would like to have not only robust pulses, but maybe very short pulses to beat decoherence. And so, and usually there are many more constraints that you have to take into account when you optimize such pulse sequences. And oops, to forward like this. Okay, so actually let me start out with just the basic elements. So just the 9-degree pulse, which appears in many of these sequences. But usually the sequences are more complicated. So rather than just a single 9-degree pulse, you have maybe a sequence of pulses, and then maybe some period, some detection period, where you try to acquire some signal. And actually, it turns out that these pulses are not really independent. Of course, there's a very sort of well-balanced interplay between them. And it turns out that if we optimize such a pulse sequence, we could optimize individual pulses, but there is some cooperativity which we can exploit between these pulses. And if we understand this cooperativity or the opportunities this cooperativity gives, that can help us to make shorter pulses, more efficient pulses, and so forth. Okay, so next sort of complex level of complexity, we not only have a single spin, we have several spins. Here I and S could be like a different nuclei, one could be an electron, one could be a nuclear spin. So usually we have pulses applied to different kinds of spins. And again, here also, if we understand opportunities to exploit cooperativity between such pulses to make the overall performance of the sequence better, we should definitely use these opportunities and try to improve the sequences. Here's actually a whole range of pulses, which in this case represents, for example, a decoupling sequence, could also be like a dynamical decoupling sequence in sensing, where also usually one has, for example, sequences like CPMG sequences of 180-degree pulses. However, and we could optimize these individual 180-degree pulses, but overall it turns out you can improve the performance if you not focus only on individual pulses when you optimize, but really optimize the whole pulse sequence. So that's another level of cooperativity that one could take into account. Then typically also we not just have a single experiment. For example, in NV centers, you have probably hundreds of experiments maybe that you accumulate, or maybe a few, but anyway, usually it's not just a single shot experiment. So repeat the experiment, which also gives additional opportunities to, for example, cancel unwanted signals by phase cycling, for example. And so basically in the end, you would like to have this sequence of pulses, of basically this sequence of experiments that you repeat. It doesn't need to be the same sequence. It can be different phases of the pulses, which you average. It can be different pulses, different pulse shapes. So again, we try to have a cooperativity of these different experiments such that the overall performance, the average performance, is as good as possible. So these are then it gives another opportunity for cooperativity and also between different scans. Today I will focus mainly on this, on the cooperativity between the pulses in the single scan, but also these other ideas have been explored and realized, and all are important to consider basically when you design an experiment. Okay, here are a few references, and of course later I will also send you the presentation, so you don't have to take any notes now about these different cooperativity ideas and different aspects. So in the talk, I would like to first kind of remind you of the most important experimental imperfections to take into account, some important conventional pulse families I would like to introduce as a reference point so we can compare with previous approaches. I will introduce a little bit more formally these cooperative pulses, some important concepts in this relation. I will show you how we can increase performance due to additional degrees of freedom, basically, that this gives us in the optimization. And the main applications I would like to focus on today then is Ramsey experiment and the Hahn echo sequence. And maybe if I have time, I can show you some further examples of such cooperativity and maybe also hint at some subtleties and technical details. Actually, I was just talking to Alistair during lunch today, and so when I prepared this talk, I went through through these papers we wrote, which I sent you, which you probably have looked at, and it's actually amazing. So there are a lot of technical details in there, and so in this talk I will mention some of the details, but I will focus more on the general idea. And if you are interested in some more details, I'm happy if you contact me. I'm happy to help you and explain this in more depth. Okay, so again, let's jump back to the single pulse case, and so let me just show you typical inhomogeneities that we have here. So if we actually, I'm not even sure if I can. Well, probably I need to go to presentation mode. Do you think it's okay? Okay.
Yeah.
Can you still see the presentation?
Yes.
Yes.
Yeah.
Okay. Good. Okay. So here is the effect of a 9-degree pulse, where I try to excite a spin from out of the Bloch vector from the z-axis, for example, to the x-axis, and so that's the ideal case. I switch on the pulse and the magnetization goes from Z to X. So that's how it should be. However, in practice, our coils or our devices that create these fields, for example, microwave fields, radio frequency fields, laser fields, they're not perfect. So we have some inhomogeneity. And in the case of NMR, usually we have a kind of macroscopic sample. But also in some NV center experiments, you also look at really ensembles, like a whole surface, not at an individual NV center. So some centers, depending on how far away from the antennas, may feel a stronger field, and some will feel a weaker field. Or actually, even if you have a single center, a single quantum system, depending on the time of day, maybe there's some fluctuation of the field strength. So it's some, or maybe, I mean, it's not perfectly calibrated. So always we never know exactly the amplitudes of fields. So there's some variation that we need to be robust to. So here's if the pulse is not robust, if we just use a rectangular pulse, and so if we excite the spins now, some spins rotate faster, the right spins, and some slower. So if we think we give a 9-degree pulse, some spins reach the equator, but some don't quite reach it, and some actually overshoot. Okay. In general, then also we have not all our spins. We have usually several spins, and or also due to calibration, it's never perfectly calibrated, so you're never on resonance. And in many cases, you have many spins at the same time, so you have a large range of offsets to cover. And so basically, you also have some frequency offsets to take into account. And so here's the effect of what frequency offset does. Basically, the spins, depending on the frequency they actually have, behave differently. Only the spins on resonance reach the equator, and the spins off resonance spins go basically back to the z-axis. And of course, in practice, you have all these effects. I mean, these are kind of extreme cases, but just to illustrate the point. And in some cases, actually, the cases are as extreme. Consider, for example, here for the V1 heterogeneity, a sample in an EPR experiment, which is in a resonator, and there are nodes, and so where actually the signal is very zero, and there's what is the opposite of a node?
Antinode.
Antinode, exactly. Thanks. So basically, then you have very strong pulses, and so there can be quite large variations in such experiments. And the combination of this actually looks then like this. So basically, when you think they give a 90-degree pulse, you may be all over the place. And what we need is now some robustness to really have good sensing experiments, good spectroscopy experiments, whatever you do with your pulses. Actually, here's time-lapse movie of a flower in our garden, which I took some time ago. So basically, it reminded me of this not robust pulse sequences. Okay, so that's the kind of implementation or the kind of imperfections we need to take into account. However, there are many more. There can be temporal fluctuations. There can be rotations of the sample, like in solid state NMR experiments. There's noise, all kinds of imperfections we need to account, and these are just the most important ones. Before I proceed, I would like to remind you maybe, and maybe for some of you it's not so obvious, or you're not so familiar with these concepts of basically 2 or 3 different main families of pulses, which we, on the one hand, we have so-called universal rotation pulses and point-to-point pulses, and different flavors of these. And for the following, particularly when we compare our cooperative pulses with conventional pulses, we need to know what these conventional best pulses are. And actually, before I go into the details, or at least try to illustrate this with some illustrative examples, here are a few references for point-to-point pulses. So this goes back to 2004 for so-called Iceback pulses, which I will briefly mention, and so-called universal rotation pulses. And so here's just an example. Actually, if we look at these, at such pulses, what we, in this case, it's excitation pulses, point-to-point excitation pulses. What we see is that for a certain radio frequency amplitude, in this case 10 kilohertz, where if we want to have an efficiency for a certain bandwidth, where we align the magnetization vectors basically to the x-axis as closely as possible. So the efficiency in this case is measured as the projection onto the x-axis, and then we see it basically as a function of the offset range for which we achieve this efficiency of 98%. What is the minimum duration? And so basically this is a typical picture of optimized pulses. Typically, the pulses get better if we allow for more time, if the pulses can be longer. But actually, it's quite a dramatic change compared to previous like composite pulses, conventionally optimized pulses in NMR. All this has no cooperativity in it. It's just, so what we see here is basically the difference between conventional, typically designed excitation pulses compared to optimal control type pulses. And so here is actually a picture of a highly optimized pulse that, so I call point-to-point, and I will show you in a second and the difference to these more general universal rotation pulses, where here we see, again, all kinds of magnetization vectors, or Bloch vectors along the z-axis initially, and we want to bring it along the x-axis, and this is done here by just a rectangular pulse. And basically, so it's not a sophisticated pulse, just a simple pulse. And basically, it corresponds to our flower that we have seen before, except that now the vectors are spread. This is from the front to the back. That's the amplitude of the control field, scaling basically, and this is different tunings. And for on-resonance case and perfect calibration, basically the spins along the x-axis. And down here we see a pulse, complicated pulse that was optimized. And this just illustrates like what such an optimized pulse, again no probability, does with this whole range of different spins, different offset frequencies, different scaling of the RF amplitude. It's just a highly orchestrated dance what these block vectors do. This of course is simulation, but when we do experiments, actually we can exactly reproduce, basically we can exactly measure for each offset this particular the end of the pulse. And the spins are not perfectly aligned, but pretty much aligned along the x-axis as they should be. So much better than this. So these kind of conventional optimal control approach pulses or optimized pulses that we considered. And what I showed you is just an example of what we call a point-to-point pulse, where basically if you look at the Bloch sphere, we start with a Bloch vector at one point, basically in this case at the North Pole, and want to bring it to another point, which is on the equator, which is the x-axis. Okay, so we're going to go from z magnetization or z vector to the x vector. Now, as opposed to this, for universal rotation pulse, we don't define the initial point and the final point on the Bloch sphere, but we define some rotation axis and rotation angle. So, for example, if we have a 90-degree pulse, we want to have an effective rotation around the y-axis, so 90-degree y pulse around the y-axis, and the z should go to x should go to minus z, and y should stay where it is. See here, we only considered one vector, and we have no idea what x, y, z do. And in most cases, in many cases, actually, this is completely fine. We are only interested in this one point-to-point transformation. However, for example, if you do some refocusing pulses, echo experiments, for example, then we need such universal rotation pulses to really refocus the magnetization independent on where it is originally. Now it looks like there's no big difference between the two. So I mean, here it's a 90-degree rotation, here it's a 90-degree rotation. But I try to illustrate this a little bit clearer. So if you have a three-dimensional object, suppose you have this little LIGO plane, and let's look at the universal rotation, the ideal pulse basically. If you rotate around the y-axis by 90 degrees, then the LIGO plane kind of flips down, and so the noise points to the front. If we now optimize a pulse according to this criterion, so universal rotation pulse, it tries to match basically this the coordinate system then in the end to the desired coordinate system here. And so this is basically if we optimize such a pulse and apply the corresponding rotations for different offsets and different V1 scaling, we see this picture. So we more or less recover the plane. So the nose is where it should be, the wings are where they should be, and so forth. If we actually do the same thing for a point-to-point pulse, actually here it's a nice example where we have additional degrees of freedom, because for such a point-to-point pulse, we don't care where the wings go. And actually, if you optimize such a pulse, also the algorithm doesn't care. Of course, you have to choose the proper figure of merit and the proper gradient calculations. But I mean, basically, the nose of the plane points along the x-axis as it should, but we don't care where the wings are. So basically, in this case, we have not. I mean, one solution actually to go from z to x is to rotate around the y-axis. However, for example, if you rotate around the vector between the z and the x-axis by 180 degrees, you also get to the x-axis, and there's actually an infinite number of solutions that brings you from z to x. And these additional degrees of freedom that you have here, basically in the end for applications, translate into shorter pulses. So if you need to go from z to x, you could use universal rotation pulse. But if you don't need it, don't use it. I mean, optimize better point-to-point pulse, and you can do the experiments much faster. Okay, so up here it's a case of basically a random pulse which has no robustness at all. Okay, similar things we can do with 180-degree pulses, so around the x-axis, point-to-point pulse. You actually don't care about the axis, you just go from z to minus z. Universal rotation pulse actually would kind of respect the rotation axis. So would have, for example, this case. And in terms of this LIGO plane, here we have this inversion. Here in this case, basically the nose is pointing down, but again, the wings are, we don't care where they look at. And these are some experimental results where we actually check that some of these, for all these different offset ranges and scalings of the control amplitude, we get the proper performance of the sequences. Okay, so these are the two main families, the point-to-point pulses and universal rotation pulses. And with respect to what we want to talk about today, about basically the cooperative pulses, there will be an aspect of also inherent time evolution in a pulse, which we in the end, these kind of pulses I call Iceback pulses. And just a brief summary, basically. So if you have a pulse that brings everything, for example, from z-axis to the x-axis, these are the pulses we considered so far. Actually, there are, I mean, we've seen we can find good pulses, but still they're quite long. It's very hard to actually achieve that. It turns out that it's much easier to find pulses that are already, I mean, where the magnetization or block vectors are already kind of dephased after the pulse. And in many experiments, actually, you don't care, it's fine. So basically, if that is easier to do, or you can do that faster, that's something to consider, to have these defocused pulses, highly defocused, pre-focused, highly pre-focused. And the interesting thing about the pre-focused pulses is that basically the orientation of the block vectors is opposite to what they would be if they would just dephase during the delay. And this is shown here. So basically, in-phase pulse, at the end of the pulse, in this case, all the phases are 0. Here, they actually, so this happens for the dephasing, but in these pre-phase pulse or pre-focused pulses, basically the phase slope as a function of offset is opposite. And in the end, basically, what you can do then is to, so this is shown here. If you have these pre-phase pulse, if you just wait a little bit, everything comes back in focus during a delay. So you can have an echo after a pulse, so basically to eliminate dead time problems. And these are these defocus pulses, basically. And depending again on the application, you can use one or the other. Actually, it turns out that easiest it is to optimize these defocus pulses. Even though it looks more complicated, it's also relatively easy to optimize these pre-focus pulses, and the hardest is really to have these in-phase pulses. So if you don't really need them, try to do it something else. And yes, actually, and just one final concept that we'll also come back to is kind of an effective evolution time under the offset terms and maybe heteronuclear couplings during the pulse. So basically, there's no evolution time in this in-phase pulses. Here, it's like part of the pulse, in this case, about half the pulse. We already have this sort of dephasing. Here it's during the whole pulse duration, and here during the part of the pulse or the whole pulse, we have basically a negative evolution period during this pulse. And so this ratio of evolution period over the pulse duration is what we call the R factor, and we'll come back to this a little bit later. Actually, an interesting point, that's where the name basically comes from. So in many experiments, suppose you have some evolution period that you're interested in, so here and here. If you, and this could be an evolution period, for example, in a Ramsey experiment or an echo experiment. If you have a pulse, excitation pulse with the evolution period, effective evolution period inside of 0, basically the evolution starts at the end of the pulse. But actually, you can also shift this into this period and have part of the evolution already during the pulse. So basically, overall, you can decrease the pulse duration. So in this case, actually, with these refocused pulses, the pulse duration or the pulse sequence duration would actually increase. And so it's just a kind of a schematic picture. So if you keep this constant and only look at in-phase pulses and try to make the pulse as short as possible, or the overall sequence as short as possible. So we squeeze the duration of this pulse. So it's getting harder and harder to optimize for, because the pulse sequence is getting very short. And so it's much better to, so up here is this as a pulse where we have some of the evolution period inside the pulse. So basically we can shift this into the sequence and reduce overall pulse durations also. And it's a little bit like an iceberg if you try to compress it up here, but you stop it at a certain limit to what you can do. But if you put this in some water, basically you have it sink to a level where it's comfortable. And so it's basically only part of, just like an iceberg, only part of a pulse works outside of the evolution period. And so there's a nice acronym for this, and it's called Iceback pulses. Okay, so now we have looked at these that's sort of standard sequences. So basically you can think of conventional composite or optimal control pulses as pulses that try to compensate their own imperfections. Now in the cooperative pulse approach, basically we optimize basically the robustness of an entire pulse sequence. And so basically the pulses are supposed to not only compensate their own imperfections, but actually they don't need to be perfect. They can also sort of compensate each other's imperfections. And so one example is the Ramsey experiment, actually, that we will look at. There are some important concepts, basically. So of course we need some optimal control algorithm. So we typically grade algorithm. We need some. Typically in this experiment, we need to consider some filter experiments, and I will come back to them. So in experiments, these often correspond to phase cycling that kind of filter out certain unwanted signal, typically based on coherence order. For the analysis of the pulse sequence, actually it turns out that Euler angles are extremely convenient and very powerful. It's something I will touch on a little bit. So they help to analyze the degrees of freedom in pulse families. And typically, the more degrees of freedom we have in the optimization, the shorter the pulses are in the end, the better the performance. And we can also do something like offset-dependent effective evolution periods. Okay, and so as right now, so we look at Ramsey sequences, Hahn echoes, and maybe some other applications in the end. So let's start with the Ramsey building block. In this case, you have two 90-degree pulses separated by a delay, which is called tau here. And we consider here a 90-degree pulse for the excitation and a 90-degree minus y pulse to flip back the magnetization towards the z-axis. Okay, before we look at this, let's at this experiment in more detail. Let me briefly introduce to you the Euler angles. So basically, whenever you have a rotation, you can represent this rotation by three standard rotations. One rotation around the z-axis, one rotation around the y-axis, and the third rotation around the z-axis again. Actually, there are many different collections of combinations of rotation axes for these Euler angles, but these are the typical ones that are used in quantum mechanics and that we also use, and that turned out to be very, very useful here. So basically what one can do, but whenever you have an initial orientation, so initial coordinate system, initial object, or initial, so it's again a LIGO character, little astronaut. If you rotate this, so here's x, y, z axis. If you do a rotation around this vector r, this rotation vector, which is defined here in terms of theta and phi, and this rotation angle minus 140 degrees. So if you rotate around this, basically you end up with this position of the astronaut. And whenever you have such a rotation axis and rotation angle, basically you can always calculate very in a straightforward way numerically these three Euler angles. And here in this case, basically we first have rotation around the z-axis by 125 degrees. So that brings, so here's the z-axis, so it rotates the astronaut around the z-axis. Historically, the first, and I can explain this, but I don't want to go into details here. The first rotation angle is usually called gamma. The second is beta. So here we will rotate around the y-axis, and then a final z rotation, in this case by 139 degrees. then we end up exactly at the overall rotation that we wanted to decompose. And decomposing rotation into these Euler angles, actually, usually it's considered to be an old-fashioned thing. Nowadays, like if you do computer graphics, everybody says, no, don't do Euler angles, use quaternions. They are have much nicer properties, and I completely agree. So for many applications, quaternions are nice. And actually, we in quantum mechanics, we always use quaternions because whenever we talk about a propagator, time evolution operator, usually it's described in terms of a unitary operator, unitary rotation operator out of SU2, and basically the elements of this operator basically are made out of quaternions. However, in many applications, like these rotations around the z-axis, this is something you get for free in most of your experiments, because rotations around the z-axis is what you get when you have just free evolution, so due to offset, and only and the y rotation, that's something then sort of the essence of a pulse really. And so now let's look at the analysis of such a Ramsey experiment in terms of these Euler angles. So in the Ramsey experiment, we have two pulses, so I showed before. So usually there's 90-degree pulse, also 90-degree pulse, and some evolution period before. So the first unitary operations of the first pulse, you can now decompose in terms of this z, y, z, so gamma, beta, alpha rotation. And it turns out if you have some pulse, I mean, if it's an ideal pulse, these rotations are independent of the offset frequency, but a real pulse, I mean, the rotation angle and axis will change as a function of detunings. And so basically also these alpha, beta, gamma angles change as a function of detuning. Then you have your evolution period. This gives you a phase of omega tau, rotates also around the z-axis. And then you have, again, gamma, beta, alpha for the second pulse. First thing you see is, I mean, the first pulse and last pulse is shaded in gray. Basically what we do in our Ramsey experiment is, so we start with the Z Bloch vector, we excite it. During this delay, we let it precess. And then we give another rotation, and depending on where the magnetization now has ended up after this precession, maybe either it's flipped back or maybe if it stays in the plane. But basically in the end, we just measure the Z component. Like for example, if you do an NV center experiment, you can only measure the Z component. But if you do an NMR experiment, you can do some filter to just also let the component survive. And so there, basically, what it tells you is that on the one hand, because in the end, or let's start at the beginning. If we start with the z-axis, this initial gamma rotation around z doesn't do anything, so we can neglect it. So it doesn't just it's completely transparent. Basically, it doesn't do anything to our experiment. Also, since we want to end up with the z-axis in the end, we filter z. The final z rotation also has no effect. So basically, we can't ignore this also. So it's kind of shaded dark. Here's the sequence of transformations. So we start with our initial Bloch vector, again along the z-axis. And now we're interested only in the z component of the final magnetization as a function of offset. Now there are these different transformations. Again, gamma is gone. We just have the beta alpha transformation. Here's something which is abbreviated as SQF, single quantum filter. So basically that what that does is if the first excitation is not perfect, so if we don't end up at the equator, we just delete everything that's not in the equator. Basically, it's a so-called single quantum filter. So the Z component is a zero quantum term, which we just eliminate. And so basically that simplifies the picture. And in the end, also we eliminate the X and Y components. We just focus in the end at the Z component. And that's exactly what you want in the experiment, because I mean, at this single quantum filter during this detection period, you only pick up information about precession, or you only measure basically field strengths with the transverse component, or whatever is in the along the z-axis doesn't give you any useful information. And that's why I usually eliminate these terms altogether. Okay, then one can proceed, and here I don't want to go too much into details, but just to give you a flavor of the analysis. So you see here we have 3 Z rotations, and of course they all commute or can all be combined. Also, the single quantum filter, it's something which commutes with the Z rotation, so you can also put that in front. So basically, you can express your final Z magnetization as a function of basically the beta angle of the first pulse, the beta angle, actually sine of these angles of the second Ramsey pulse, and cosine of this overall evolution. So here appears the offset frequency omega, the first Euler angle, the alpha angle of the first pulse, and the gamma angle of the second pulse. Okay, so in the ideal case, basically these two beta angles should be 9-degree pulses or minus 9-degree pulses. So basically we can continue to analyze this, but we can, next step to do is to decompose these alpha angles, alpha and gamma angles, in terms of their linear contributions. So before I showed you these Iceback pulses, so in the simple case, we just have a constant phase as a function of offset after the pulse. You could have a linear phase, which then could, linear is always good because you can, if the slope is right, or if you apply a refocusing element, you can always refocus this and get an echo. So that's how to get an echo. But in general, there are also nonlinear terms which are indicated here, which are kind of taken out here. And so we can write the final magnetization in terms of all these terms. Some of them we can contribute, can combine. And basically here we get then this Ramsey condition that the sum of these nonlinear terms has to be 0 in these Ramsey experiments. So if we combine this and actually define delta, it's actually a time, as these orange terms. So this R factor of the corresponding to the alpha angle times the duration of the first pulse and this factor, then we get basically a time shift, which, as you will see in a second, corresponds to a small translation of the echo. And in many cases, we just need to know where the echo is, but this translation could be 0. Delta 0 is fine, but usually delta non-equal 0 could also be good. And it turns out sometimes there's a sweet spot for the optimal delta, which gives us the best or the shortest pulses for the best signal. And so basically this is shown here. We have an effective evolution period for such a pair of pulses. There's the yellow part evolution. There's actually the tau separation of the pulses. But since some of the evolution is taking place during the pulses already, that's basically this delta part, which is then there. And so I can define then this delta exactly in the overall R factor for this sequence. Okay, so here we can now define a figure of merit. So in the end, we would like to have the Z magnetization as a function of omega as close as possible to some target function. And usually it's just a cosine modulation, so-called Ramsey fringes. If you have ideal pulses, delta pulses, everything is perfect. You get nice cosine modulations. And this is basically this cosine modulation that you want to measure. So basically the target is this cosine thing. Can have also some sines which we can absorb into some of the detection phases and things like that. It's another degree of freedom, but I'll go into this here. So once we have these figures of merit, we can then define different so once we have this figure of merit, basically we can then define so-called, or can calculate the so-called co-state vector at the end of the pulse sequence, which we can calculate backwards. And if you have the evolution of your Bloch vector and of your density operator forward in time, and the evolution of the co-state vector backwards in time, actually taking into account these filter elements, then basically you can very efficiently calculate the gradient of the whole pulse sequence. So that's kind of very similar to a standard NMR experiment. And here is basically a series of optimizations where we try to determine now this sweet spot for this R factor, or this basically this evolution period delta, where so we this R factor can I told you it can be negative. Here we just consider positive cases. But it's kind of as a function of this R factor, if we do many different optimizations, then we find kind of this plateau, and there's somewhere a maximum. And basically that's kind of the sweet spot I was talking about. If we optimize a pulse sequence for such an echo, in this case for Ramsey experiment, we would like to do it in this R factor. And here are some results. These are typical examples. In this case, actually a pair of pulses for the excitation and for the de-excitation of Lübeck pulse. Here's the X control, here's the Y control, and so this pair actually was optimized for. So actually the pulse duration was 75 microseconds. R factor 0.53, so there's effective evolution period about half of each pulse at the end of this pulse, beginning of this pulse. So that's our effective evolution period. And even though we did not in this case impose any symmetry constraints on the pulses, actually turned out to indicate here the second pulse. If you look at this, it's about the same. It approaches very closely the first pulse if you time reverse it and shift the phase by 180 degrees. So basically, if you look at this thing, and basically this is the same as this, shift of 180 degrees, you change the sign of these things. So basically, you have symmetry. This is symmetric to this, and so forth. And also here you see this nice symmetry. And so basically, if you would like to answer, discuss all these symmetry aspects, so it's very interesting, and we did that in the paper. This is what I would put in the category of subtlety, so it takes quite some time. And if you're interested, I suggest to go in the paper, but also you can, of course, contact me anytime to explain this in more detail. Okay, so okay, I mean, I just briefly show you one can analyze then the Euler angles for such time reversed and phase shifted pulses, and also there are similar families for time reversed and inverted phases. People have suggested a lot of different combinations of such pulses, and one can analyze them very nicely. Turns out that if one has a bunch of such symmetry-related pulses, if one analyzes now what does our Ramsey condition boil down to, in the end, so there it's particularly nice. So I mean, in this case up here, what we have is we have relation between alpha and gamma. So all alpha and gamma angles play a role, except for the last three that they depend only on alpha. So that already simplifies. So we have 1 degree of freedom. The gamma angle we don't care about. Actually, it turns out. So this, for example, is relatively restrictive. Here, with the nonlinear part of this of the alpha angle, nonlinear offset dependence has to be 0. So again, it has to be has to have a specific value. However, in this case, actually, for the time reversed and phase shifted, that's the kind of pulse that we find in the optimizations. Actually, turns out that there's this nice property that the nonlinear term doesn't even have to be 0. It just should be symmetric, basically, with respect to the offset frequency. And it turns out it's only yes, in the end, so that makes this a very naturally nicely fitting family of pulses, and one can actually directly could optimize directly for such pulses with such symmetries. So actually, I'll skip this. I'll just show you an example. So basically, this curve here is actually that's such a highly optimized pulse. What it has is so the solid line is the offset dependence of alpha as a function of the tuning. Basically, it's this curve. What we can do, first thing is to find a linear approximation of this. So we can have fit, so we should go also through 0 as equal to 0 to 0. So we can subtract that, which leaves us with this. So actually, you see here, this sequence is a symmetric sequence, and with the analysis of these Euler angles, we can show that symmetric nonlinear terms are okay. So they don't play a role. And in the end, it's only these antisymmetric. So if you subtract the linear part, this is just this endosymmetric part, the A in the subset, subscript, which ideally should be 0, but here you see they are extremely small. So compared to the other values, actually it corresponds to a fraction of a degree over this whole offset range. And basically this fulfills, in this case, this condition for the Ramsey experiment. So basically one can then do such tables, and what you see is, for example, if you compare universal rotation pulses and different symmetry-related so second pulses, all these parameters here have to be 0, so they have to be fixed. So it's very difficult to achieve. If you look at combination of point-to-point or point-to-point with this R factor not equal to 0, actually it turns out that this gamma angle already is free, so it's easier to optimize. Here, this depending on what R is, this has to be 0 or not. There's another family which I did not particularly, specifically go in. It's also described in the paper. But in these, if you have now these cooperatively optimized pulses, actually neither gamma, this R factor, the symmetric part, nor the nonlinear antisymmetric part is fixed. Just needs to have some symmetry relations. But that's this actually gives us extremely good performance. And so here's kind of the crucial figure, which I'm happy to come to now, which shows you basically what we gain really by taking this cooperativity into account. So here we have figure of merit, our quality factor, which we would like to have 1. So basically a logarithmic plot. What it shows is, or what it represents is how well the final Z magnetization as a function of offset actually matches the desired Ramsey fringe pattern. And so here, if we try to optimize pulses for such experiments, what we could do is we could optimize perfect universal rotation, so perfect UR 90-degree pulses around the y-axis, flip down, flip up, combine them, and then see how well we match this Ramsey fringe pattern. And you see it's extremely bad. So we need even 400 microseconds pulses in this case. So the pulse amplitude is 10 kilohertz again. Just as a reference, the 90-degree pulse has a duration of, in this case, of 25 microseconds. Here. So for very long pulses, we get very poor performance. So don't use universal rotation pulses if you try to set up a Ramsey experiment. Turns out point-to-point pulses are sufficient if you analyze this. And basically that's what this previous analysis kind of tried to summarize. So for the same duration of pulse, for example, 400 microseconds, you get much better performance. You already at 99.9% efficiency, which sounds good, but still the pulse is relatively long, and it's not that great, actually. I'll show you in a second. Actually, what's nice is that in this scaling, you see that the performance more or less scales linearly with the pulse duration. Now, this is, if you use cooperativity, still with R equals 0, where basically all the evolution has to happen in the delay between the end of the first pulse and the beginning of the second pulse, so where nothing is shifted inside the pulses. So again, much faster, basically with much shorter pulses. For example, rather than 400 microseconds, you just need 200 microseconds to get more or less the same performance as these point-to-point pulses. But we are not yet at the sweet spot of this delta, of this R factor. If you now, and in particular, actually, what was surprising when you first compared this with conventional pulses, I mean, for this short pulse duration, the rectangular pulse was much better, which was quite surprising initially. But actually, it's not a point-to-point pulse with R equals 0, because during a rectangular pulse, actually during a certain fraction of the pulse, actually it's 2 over pi, so it's a fraction of the pulse in which there's evolution, so the spins already dephase. And so we can now also optimize pulses that do the same thing with the R factors in the sweet spot. So this is these are these Iceback pulses which we can combine without cooperativity. But if we now switch on cooperativity and optimize these pulses with cooperativity and the sweet spot of this R factor, or this effective evolution period, basically we find this. So basically at extremely short pulses, just 3 times the duration of a 90-degree pulse, we are at insane fidelities, which basically translate in perfect excitation, a perfect reproduction of this Ramsey fringe pattern. Here's actually to give you an idea what that translates to. So these are just the pulses, for 75 microseconds. The rectangular pulse actually, that's what you expect. So actually close to resonance, it nicely follows this Ramsey fringe, but for large offsets, it does not. It's not able to bring the spins to the transverse plane. That was this flower kind of simulation that I showed you initially. So this optimized Iceback pulses, they actually quite, fidelity is not bad, so it's better than 99%. But you see, it's also not great, so it's still some percent away from the ideal Ramsey fringe. But if you do this cooperativity pulse, basically there's no difference anymore. And just for comparison, also these are like universal rotation pulses for the same duration. They're just crap, so it's not possible within this time to get a perfect Ramsey fringe pattern. And here are just some examples of such pulses. So we see the evolution. Basically, we have initially all the maximization vectors or Bloch vectors along the z-axis. Here's the time point. We excite the spins. We apply the filter, so now everything is in the transverse plane. Now we flick back and now we apply a Z filter. So the only thing that survives that we're interested in is the Z component of these vectors. So basically, this is the case of the rectangular pulses. So we see, as we've seen before, so we get the Ramsey pattern, but only close to resonance. And this is what happens during such a optimized cooperative pulse. So we excite the spins. So they're actually almost brought into the transverse plane. So the fine projection doesn't do anything. It's a nonlinear phase, so it's not an Iceback pulse at all. Finally, the maximization vectors look like they point over. They actually do point all over the place. But the nice thing is that if you just now again filter out the Z component, you have this perfect Ramsey fringe pattern. And so we applied this to many complicated NMR experiments, very broadband pulses, and it works beautifully. We get basically perfect phase, and I hope these kind of experiments will also get used in sensing, quantum sensing experiments, where Ramsey experiments are also an important tool. These are just some experimental results where we apply such pulses or replace to a set of 9-degree pulses in so-called Rose experiment. Here's close to resonance, where the signal is good also in conventional experiments, but far off resonance, basically, here you lose all signal and you get a huge increase in sensitivity. Now, I have prepared a little bit about echo sequences. How long do we plan to have the seminar? Pardon me? 2 hours, okay. If I hear any protest, I can make it shorter, but I'll continue a little bit with the echo sequences, and then we can also have some discussion. And of course, I'm happy to answer questions. So the Ramsey experiment was the first experiment where we considered, where we implemented and really analyzed this idea of cooperativity. And there was this huge gain in efficiency. So now we looked at other cases, and just to spoil the result. So in the echo experiment, you still gain. It's not as dramatic as in the Ramsey experiment, but still, if you know how to optimize these pulses, you better use them. It doesn't cost you anything in the experiment. It's just more robust and shorter, basically. So here, the main reason why we started with the Ramsey experiment, it was very simple. We had this kind of, just these 9-degree pulses. So the Ramsey sequence has inherent symmetry anyways, which makes it a little bit simpler to analyze. So the next step, and actually we have gone quite a bit farther than the Hahn echo, but let's focus on the Hahn echo now. There we have a 9-degree excitation pulse and a 180-degree refocusing pulse. And actually what I have not stressed in the previous experiment, where we also had this delay, which we can vary now in this Ramsey experiment, and we also have this delay, actually due to the fact that we have these filter elements, which we can always do. So we can always filter, have the zero quantum filter or single quantum filter or whatever. that actually allows us to get very clean spectra in the end. And in particular, what it also does is that the echo signal, suppose you have no decay, if there's no decoherence, the echo signal that you get by such pulses and also some such optimized cooperative pulses then is independent of the delay separation. So basically what we can do when we don't, what we did not want to have is to have, of course one could do that, but we didn't want to have a sequence where you, for each separation of the pulse, you need to optimize a new pulse basically. Here it's a very general, these cooperative pulses can be used everywhere. And so basically when you optimize them, you just optimize them, for example, for tau equals 0, and then they work for any tau. Okay, so here we have this echo sequence. Again, that's the ideal case of kind of delta pulses, where we have a tau delay between our pulses, which are assumed to be infinitely short in the ideal case. In real life, of course, they are not. And then there's this tau period, and after this tau period, we have this refocusing and focusing effect on these echoes. And here's just, I'm not sure if you are familiar with phase cycling or with this filtering. Basically, what we do here in this hard echo sequence is we create a coherence order selectivity or certain coherence order pathway. It's kind of standard thing to design pulse sequences or phase cycles for such filters. So here, whatever the pulse does, actually we only allow a change of coherence order. Z magnetization is 0 quantum coherence. We want to go to ±1 quantum coherence. Actually, in this case, only to +1 quantum coherence, so to I+. And the refocusing pulse brings us from I+ to I-. And in NMR, that's what we detect. For example, in V-center experiments, you have to do some flipback to the Z-axis to measure then the echo signal. Okay, and so rather than now starting with all the theory, let me first give you a few results. So these are as a function of detuning now the different echoes. Basically, that's so if you're on resonance, we get nice echo, but if we have a larger detuning, then the echo signal gets weaker and weaker. Maximum pulse amplitude was 10 kilohertz in this case. So overall, we look at a frequency range of 50 kilohertz, so 5 times the maximum Rabi frequency. Okay, so this is what you get by. Okay, now Wolfgang is hidden. Can you? Okay. So this was basically a sequence. If you now optimize a pulse, but without cooperativity, so you try to maximize a 9-degree pulse and a refocusing pulse, and even take nice combinations. But now, if you do now if you do cooperative pulses, you can get basically very clean echoes as a function of detunings for a large range of offset frequencies. And here's actually a picture that shows you kind of visually how this cooperativity works, how one pulse can compensate imperfections of another. So in an ideal echo experiment, if we start with Z, suppose we have a 9-degree Y, 108-degree X ideal sequence. So the Y pulse brings Z to the X-axis. So we get at X, yes, actually we'll look at this in the case. And in the second, actually what we consider is just different cases. So we consider then the case where the excitation pulse has a phase error. We look at the case where the refocusing pulse has a phase error. Then, of course, if we have phase errors in the excitation and refocusing pulse, it's even worse. But let's actually see what happens, or that's at least what we expect. So ideal case, Z goes to X. 180-degree rotation around the X-axis leaves the magnetization here, so we are at the X-axis, and we want to have that behavior for all offsets in our range of interest. So basically, for all offsets, the ideal pulse, rotates the first rotation is around the Y-axis, and the second rotation around the X-axis by 90 and 180 degrees. Now, if the first pulse has a phase error, maybe not for all offsets, but for some offsets, actually, for this case, actually the magnetization does not end along the X-axis, but the phase error is phi. It ends up with angle phi away from the X-axis. If we now apply a 180-degree x rotation, so it rotates around the x-axis, so it ends up here, but not along the x-axis where we want all the magnetization vectors to end up. Let's look at the effect of, so pretty bad. If the refocusing pulse is not correct, so the first excitation brings us to x, suppose for this particular offset it works, but the offset, offset dependence of the 180-degree pulse, which is usually actually more narrow band than the excitation pulse, it's more difficult. That has some phase error in this case. So basically, this rotates now this this pulse, not around the x-axis, but about some tilted axis. So again, it's not lined along the x-axis, pretty bad. But and of course, if both errors are there, it's even worse. Except if the pulses know about each other and can compensate each other's imperfections. So in this case, I think it's a nice illustration how two pulses, even though each pulse is not perfect, doesn't have the perfect phases, actually can completely compensate their effect. So and actually it turns out that so the condition is in this case the phase error is phi, but so it's not zero. It's not. This error is not zero, so it's not really around the y-axis. But if the rotation axis of the 180-degree pulse is at phi over 2, it's actually fine, so it's not a problem. So here we get this magnetization here. The rotation axis is at the half angle, basically, it's going here. So basically, if we rotate around 180 degrees, we end up perfectly along the x-axis, and everything is great. So this gives us this additional degrees of freedom, so the pulses don't have to bring the magnetization exactly to the x. It can be all over the place if we are able to simultaneously or concurrently optimize these pulses such that this condition basically is fulfilled. And so this now shows different families of pulses, and we then can compare their performance. So in the ideal pulse, again, the echo occurs after tau. If you use bebop burp pulses, so this bebop actually it's a pulse which brings z really exactly to the x for all offset objects. It least tries to do it as well as possible and tries to do a universal rotation pulse around the y-axis here. You also get echo after tau, where tau is the pulse separation. And with the cooperative pulse, you also can optimize them so to have the echo exactly after tau. And so here, yes, so the echo tau is just, the echo time of the echo is just exactly tau. But as pointed out before, actually, even during the rectangular pulses, you have already some evolution, shift evolution or offset evolution during the pulses. So even if you have rectangular pulses, the delta pulse limit, everything is fine, but for rectangular pulses, so basically the echo does not occur after tau, but after tau plus little delta. So we already have some additional degree of freedom that we use here, and you can use now if you use the Iceback pulse. We have some dephasing here. Then you take a little longer for this refocusing pulse to bring everything back. So again, here we have some shift of the echo, and similarly you can optimize cooperative pulses also with this extra shift here. And again, now the art is that so when we first investigated these cooperative echo experiments, the question was not clear at all. Where is the sweet spot? Is the sweet spot maybe for positive delta, maybe for negative delta, or it was not clear at all. And so basically, that's what we looked at. And again, one can analyze this in terms of the Euler angles. Maybe I'll do this a little faster here. So again, the first Z rotation we can ignore. We can also, because this is in the ideal case, the beta pulse, in this case is 180-degree pulse, we can also shift basically angles from before the beta pulse and add this to the alpha, to this alpha rotation. And so we can have these modified Euler angles where we then basically just have here the alpha rotation, which is then defined as alpha minus gamma. And again, we can look at these at the degrees of freedom. So basically, for ideal pulses, this gamma 1 and alpha 1 and alpha prime 2 has to be 0. So there's no degree of freedom. For universal rotation pulses, same thing. If we start out with a Z to X point-to-point pulse and have a refocusing pulse, and this gamma angle is free. If we use this Iceback pulse, also this alpha 1 angle has some leeway, so here's a condition, so only the nonlinear part of this has to be 0. For a cooperative pulse with R equals 0, for this delta, this effective echo shift basically is 0. Gamma and alpha are free, it's only the alpha of the second one. And if we allow some delta shift of the echo, then also they can be arbitrary. They just need to have this condition that the nonlinear part of the alpha one is the same as the nonlinear part of this alpha prime of the second pulse. And so now let's look at the results here. Just to remind you, so when we optimize now, we have this filter. So here we actually have we excite the magnetization from Z to the transverse plane. There is one quantum filter plus one quantum filter, basically, which eliminates the -1 quantum in the Z component. So basically, our tiger has to jump to this hoop. Then we have the second pulse. In the delay, we just set to 0 in the optimization. There's the second pulse, which gives us this result. Now we do -1 quantum filter, we just that's this thing survives. So that's how we optimize. And for the co-state that evolves backwards, we have the same filters. And so then we find a series of pulses. There's one subtlety which also at least I would like to briefly mention. So if you do it in a straightforward way to actually optimize how you write it down, turns out that there is enormous amount of local traps in the optimization landscape. So whenever if you optimize 100 pulses, maybe there's one which approaches the ideal Pauli effect of 1, but many are trapped in much lower figures of merit. Turns out that that's let me first show you that it can be fixed. So we kind of call this preconditioning. Basically, if you change your approach and now to 100 optimizations, basically everything and nothing is trapped in this local maxima. Basically, the effect this is related to the effect of the global phase factor. So previous papers, also Thomas Schulter-Brückner is sitting here with Thomas. We also have analyzed in detail global phases, not only in single spin systems, but also in coupled spin systems. And so a lot is known about this. In particular, it turns out that if you optimize universal rotation pulses and try to make them robust, it's very important to optimize them not for arbitrary global phase, but to fix the global phase to avoid such local maxima. Could tell you much more about this, but in the interest of time, let me just leave it at that. So in the paper, it's described in more detail, and I think there's now also references to the previous papers about these global phase factors. Okay. Now one of the things to check now when we optimize such pulses is what is the optimal delta, so this echo shift that which is the degree of freedom. And the other thing is, which was also not clear, what is the relative duration of the echo, of the excitation and the refocusing pulse. If we have rectangular pulses, the refocusing pulse is twice the duration of a 180-degree pulse, twice the duration of a 90-degree pulse. But it's not clear if that needs to be the case in these cooperative experiments. So here we did many optimizations for range of this relative duration of the excitation pulse. So for example, it's 0.5, the excitation pulse is 50% of the total duration of excitation plus refocusing pulse. So basically that's where the excitation and refocusing pulse has the same duration, but we looked at all these different ranges. So basically, a case here would be a very short excitation pulse, and we spent a lot of time for the refocusing pulse. Here is the same duration, and up here, it's where we focus more on the excitation pulse. And here's this parameter of this delta, which again was not clear. So here, if it's delta 0, we want the echo exactly after tau, which is the separation of the two pulse. That's delta equals 0. If delta is larger than 0, it's shifted to the right, away from the last pulse. and if it's fallen 0, it's shifted to the left. And so we did many optimizations in this basic parameter space, where we, for example, fixed here the total duration of both pulses to 500 microseconds. And so this is the optimum that we found. So basically, if you look at this, actually, it's a nice, I mean, it's more in perspective. So there's a nice flat plateau, but one actually can then, actually, let me just go back and find a sweet spot. Actually, it's pretty close to 0.5, a little shorter than 0.5. But it's not that it's 2 to 1 as in the rectangular pulses. Also, the delta is more, I mean, it's okay to, I mean, it's okay to find deltas with negative deltas, but the optimum was a slightly positive delta in this case. And here's similar curve surfaces for different total durations. So if the total duration is small, of course, the achievable figure of merit is small, but the more time you spend, the better you get, and the better you fill this area. And here's now, if we take the best sequences, and once you know what the sweet spot is, you don't optimize everything again. So it was just exploring really the range that is possible. But if we now optimize such cooperative pulse, we know, I mean, we optimize around the sweet spot. And so here's again the performance of here's the rectangular pulse, here this universal rotation pulses, there is point-to-point pulses, Iceback pulses, and this is the performance of these cooperative pulses, either delta equals 0, or again you gain a little bit if you shift the echo slightly in pulse sequence performance. Okay, same thing, just with exponential, I mean, different scaling. And here are some plots, what these pulses look like, and we like to look at the plot. I mean, one way to represent these plots, you can also show the X and Y components of the controls. Here's what is shown is the amplitude, basically, of the pulse. So that's the XO, and you see for the shorter pulses, I mean, basically for the excitation and focusing the amplitude. And the color is, I mean, codes for the phase. So basically, we see some smooth phase variation. I mean, there's nothing dramatic going on, so it's very easy to experimentally implement this with some arbitrary waveform generators, and it's not any random jiggling around. Here, actually, the phase, I mean, the performance here is already very good. Actually, it turns out if one doesn't like these jumps in the amplitude, we could also fix the amplitude. Here's just we didn't put any constraints on the symmetry or on the amplitude of the pulse. We just put a maximum amplitude that can be achieved. And, actually, what's interesting also, so if we go to the very short pulses, so for 100 microsecond duration, what you find is in this case, what you do is you do actually basically a rectangular pulse, so no phase modulation for the excitation pulse. And here, most of the time, is spent to find a good matching refocusing pulse, basically for the considered offset range. Okay, maybe I quickly show you this. So there's actually we have now these offset-dependent angles, it's alpha, gamma angles, and it's combined angles basically. You can translate them into evolution periods of these pulses, and actually at the beginning of the pulse and the end of the pulse, and these evolution periods are offset dependent. And actually, it's a nice visual way. And just briefly, it's probably too fast to really fully appreciate this. But maybe if you're interested in these kinds of refocusing pulses or echo sequences, it's worth to have a look. So basically, what we see here is this is a set of, actually, let's start down here. These are rectangular pulses. So excitation pulse, refocusing pulse. And this is Bebop, Iceback, cooperative pulses, and this is delta not equal 0. Basically, what you see is, so we shifted these effective evolution periods. You can always shift this to the alpha, to the end of the pulse. And so we see as a function of offset for these cooperative pulses. It's not a constant evolution. So for each pulse, actually, there's different effective evolution periods actually that happens during the duration of the pulse. But automatically, the algorithm found actually a matching period for the second matching evolution period for the second pulse. So if you want delta equals 0, actually they have to be identical. But if you have if delta doesn't have to be 0, so this can be shifted a little bit. And basically the combination of this excitation and this refocusing, basically you can also fold this over. So on the right we see the gray is the separation between the pulses. The gray on the right of the refocusing pulse is kind of the same separation. And then on top we see now the kind of the remaining effective evolution period. And see, basically it's a flat, it's a constant line. It's a straight line here in this cooperative case. So that means for all the different offsets in our range of interest, the spins rephase exactly at the same time. Whereas, for example, if you look at these Iceback pulses, so here this is pretty flat. This pulse, this refocusing pulse, has some bumps and they don't compensate. And actually, in the end, you have different effective evolution periods. So the phases also for different offsets are different of the echo, and you get some destructive interference. And so here it's inverse. And basically that leads to this nice performance. Also, here's what individual pulses do. So rectangular pulse, basically here we just look what happens if we apply a 90-degree pulse, rectangular pulse, with this 10 kilohertz maximum amplitude. With that magnetization, basically that's what we get, close to resonance, we get the excitation, outside not. If we apply 100-degree Y pulse to an X pulse, so suppose we had X at the end of the first, so the first pulse was perfect and we end up at X. If we apply 100-degree Y pulse, again, it only for small, it's supposed to bring everything to minus X, but it only happens for a very small offset range. So it's a very bad refocusing pulse. If you look at also at the visually optimized pulse, so for this Iceback pulse, so here we have this linear phase as a function of offset, which basically is a function of offset. So the final magnetization vector just in phase is just increasing, which gives this spiral pattern. And if we have this universe rotation pulse, it tries to bring for this whole offset range the spins towards the minus x-axis, but the time is just too short to really do this perfectly. Here's what the individual cooperative pulses do. Individually, again, they are not designed to work great individually, so it looks horrible. So if you look, we excite this, if we apply this to the z-axis, magnetization is all over the place after the excitation. You apply the refocusing pulse of the co-op sequence to IX, it's also all over the place. But if you combine them to an echo, this is where the magnetization vectors then lie at the end of the cooperative echo pulse. And whereas here here you have a lot more phase errors, and here the offset range where you have large amplitudes is very small. Okay, it's just a kind of a comparison of the different cases where you can get a beautiful alignment. And here some comparison between simulations and experiments for rectangular pulse, and this is for the cooperative pulse. And also you see up to very details. It's nice to reproduce basically what to expect, and also translates nicely in simulation and experiments into larger echo amplitudes and less artifacts compared to these other sequences. Okay, at this point, I think it's probably good to slowly wrap up, not to strain too much. Again, there's more things I could talk about. Let me at least mention two more, or several more applications where coercivity effects can be exploited to make overall pulse sequence performing better. One is, so many of you do probably some kind of CPMG sequences, so sequences of 180-degree pulses. Here's one application. Again, this is from NMR, where we usually, actually the sequences, or basically CPMG sequences, are used. It's so-called relaxation dispersion experiments to sense certain decoherence rates. And without going into details, so there's some surface in the end that that measures these rates. Ideally, the surface is supposed to look like this as a function of the detuning of the spins and the offset frequency of one of the spins that in this case do chemical exchange. If you replace these with rectangular pulses, so this looks pretty crummy, it doesn't work at all. But what we can do now is not, what people have tried to do is to optimize individual 180-degree pulses. But in this case, you don't have time between the pulses to do that, and you need to have a fast repetition of the pulses, so it doesn't work really. But we found a way to actually optimize entire sequence. So basically, this sequence of ideal 180-degree pulses we can replace by this shape pulse. And you see there's some structure to it. So basically, there's some kind of pulses appearing. The phase, again, this color is pretty much modulated. We didn't know what to expect in this case. Actually, it could be that we would have found some UDD sequence or some known super cycling or some phase cycling. But it turns out actually there is no reason that, for this sequence, for the structure to be symmetric. And so that turns out to be the best sequence where we then again don't optimize individual pulses, but just optimize overall the total pulse duration. And how long do we have the seminar? 4:30. Okay. Yes. Okay. Maybe I'll skip this. Another example is decoupling, heteronuclear decoupling, which is closely related also to what is called dynamical decoupling, information processing, where typically also, in the old days, or the one approach was to use, again, kind of CPMG type sequences, and people have replaced 180-degree pulses by composite pulses. One was, the early version was from the 80s by Markham Levitt, who pioneered this kind of use of composite pulses, for example, in particular in these decoupling experiments also. Turns out that, for many years, people have tried to optimize individual 180-degree pulses, but this was still the gold standard in many applications until actually a few years ago, actually 10 years ago now, we found a way to again optimize not individual pulses but entire entire decoupling sequences, and that's an example which then which has much better performance, and which here's an example of such a decoupling sequence that was optimized for now the parameter range of biological NMR experiments with very large frequency ranges at very high magnetic fields, and conventional sequences are either not broadband enough or have huge sidebands and get then very clean sequences. Again, this is simulations and experiments, so we get very nice correspondence to this. And with this, I just let's see if we missed any subtleties and technical details. So I showed you some examples how to calculate such transfer functions, which can be nicely kind of packaged in terms of these Euler angles that appear. We have conditions for Ramsey pulse in terms of offset-dependent Euler angles, effective evolution times. I showed you how they can be defined. We have, it's important to consider such appearance order filters based on phase cycling, which makes the performance of such cooperative pulses independent of the delays between the pulses. We analyzed some symmetry relations of pulses, and in particular, I mentioned the importance of global phase factors for interoperations to avoid local traps in optimization of propagators. And in this case, we used basically, in the case of the echoes, we avoided many of these traps by pre-optimizing pulses, taking these global phase factors into account. The Euler angles I showed you already. Some symmetry relations. This just to wrap up that there are many possibilities for cooperativity. I was focusing on the cooperativity of several scans. Actually, we considered the Ramsey experiment, which was 2 pulses, the echo sequence, Hahn echo sequence, which was also 2 pulses. We extend this to 3 pulses and to more pulses also in the future. We also considered cooperativity between heteronuclear sequences or pulses which apply to different spins. I mentioned these decoupling sequences. And I just mentioned, we can show you any examples, but so we can also optimize pulses for entire experiments which consist of many individual scans. Two main people, so I was digging up old group pictures. Michael Brown is here, so he optimized and analyzed the Ramsey type cooperative pulses, and Wolfgang Kallis has optimized the hand echo sequences, and he just graduated last year. And with that, of course, I thank a lot the QuSCo project and EU for financing this, and having been at the kickoff meeting, it's really great to see the spirit, and we have these secondments, and it's really it's a fantastic thing. Also, I would like to thank these other funding agencies, also the Varian NMR Center, where we did most of the experiments, and you for your attention. And if you have questions, we are open for discussions now.
So concerning the questions, the people who would like to ask questions, please write your name in the chat, and we will call each one in the order that appear in the chat.
Maybe I leave this as a teaser. Maybe it is exhausted.
Okay, so we can start with Federico because he's the first one. He wrote the name. So Federico, please ask the question. Go ahead.
Hear me, Steffen?
Yes, a little softly, but I can hear you.
Okay, maybe I'll put it louder. I think I can do that. Okay,
Yeah.
So my question is, when we saw the cooperative pulses and how they were robust to various parameters, there seemed to be some error in, especially the case of the parameter. I can't remember now what this delta was. I think the offset of the time at which you look at the echo, but there seemed to be some error, especially when the offset was 0. Is there some trade-off between being robust and being precise at the values you expect, like at the center value?
Well, it's just a matter of degrees of freedom. So if you really need to fix the echo at the time tau, so have this delta equal to 0, well, it costs something. Usually, I mean, you still get the same fidelity or the same robustness, but at the cost of slightly longer pulses, which of course you would like to avoid. But in most cases, you need to know where the echo is expected, and that you know exactly, even if this delta is not 0. So you can always adjust your experiment such. And if you have in the experiment this degree of freedom to shift the delta to the sweet spot, then, I mean, here now we know there is such a sweet spot and one can exploit that. But if for some reason you insist that at the time of the echo or the duration or the evolution in such a Ramsey experiment is exactly as like in the delta pulse limit, what we also showed is that you can achieve that also. You are still better, significantly better using cooperative pulses than individually optimized pulses. But of course, the price to be paid for this extra request basically is that the overall pulse sequences have to be a little longer.
Okay, thank you.
Welcome.
Okay, the next is Fernando.
Hi.
Yes, can you hear me?
Yes, very good.
Okay, so I had one question regarding the effects of the coherent or other dissipative effects, because so far we have not taken those into account that much. So when dealing with these open quantum systems and their effects, it is also, do we have to treat them differently in the sense that we have to optimize our pulses separately before trying to do the ensemble optimization? Or can we perform more or less the same scheme that we have presented here?
I'm not sure if I fully understood the question. Could you, so there are these two options that you want me to compare. Could you just repeat them?
Yes. When we are dealing with dissipative effects,
Yes.
we have to take those into account. And I guess for each and every individual pulse, we have to at least start with a guess pulse. That is not a very bad choice. Otherwise, I'm guessing that when trying to perform the optimization with all the pulses together, we wouldn't get so easily to the desired place. Or can we again try to perform the all-together optimization with all the pulses instead of trying to optimize each different pulse regarding the dissipative effects in its period of time?
Mm-hmm. I think I got it better, but when you say all different, I mean all different initial states, or what do you mean specifically?
All the initial guess pulses.
Guess pulses?
So the pulses that we are trying to implement.
Yeah, so maybe I am. So let me first answer. Maybe I answer your question, but let me know if I didn't quite get it. So in general, actually, so there are two ways to deal with decoherence effects. One is kind of a simple-minded approach, and of course, sort of that's where we stand with the cooperative pulses right now, which is just trying to make the pulses as short as possible. Of course, the longer the whole experiment takes, the more decoherence losses we have in general. However, having said this, so for individually optimized pulses and some processes, actually it turns out that time optimum pulses are not necessary, or I mean, pulses with are as short as possible to achieve a certain fidelity in the absence of decoherence are not necessarily in all cases the best. I mean, usually, I mean, often they are, but in some cases, I mean, one can construct cases where they are not the best sequences, best solutions in the presence of decoherence. In particular, if you have a very structured relaxation superoperator, for example, typically, actually, so suppose you have a case where T1 and T2 processes are the same. So then actually it doesn't matter where your magnetization vector points during the experiment, it's just always shrinks at the same rate. In particular, well, actually assuming that that you do some, maybe again, phase cycling or some experiments where you I mean, X and Y goes to 0. So in the unital case, if like T1 goes to Z and T2 to 0, then also one has to consider in more detail the trajectories of these magnetization vectors. But in many cases, actually, it's sufficient to ignore them and to just have time optimal pulses. But the more structure you have, the more you gain by really optimizing in the presence of decoherence. So then you, and even in the original gray paper, and you can nicely, I mean, easily generalize this also to the case of cooperative pulses. We showed how to include decoherence effects or models that you have for your system in the optimization. And in this case, then so we have many examples where sequences that are longer than the time optimal sequence in the absence of relaxation, but longer pulses, I mean, sort of create trajectories of the magnetization such that on the way to the end of the pulse, basically you lose as little as possible. So it can be taken into account. It's a little bit more expensive, but it's certainly doable. It's just that we have not really implemented this in the case of cooperative pulses yet, but it's very straightforward.
Okay, thank you very much.
Welcome.
So the next is Tian Tian.
Yes. Can you hear me?
Hello.
Hello.
Yes.
Cool.
Yes.
I'm not sure if I can formulate my question very well, or I'm not sure if I'll do this cooperative pulses. So, in the case of Ramsey, you were saying that to this R, so you tune your R to the optimal value, and R is basically the same for the second and the first pulse. Like, are they different? Because in the end, when you show this fidelity plot, it was basically 1R, right? And
Yes.
another question is, how do you okay, so do you fix, I mean, somehow you find an R and then, so like, is this like zero quantum filter or single quantum filter? Is it really necessary for like achieve this good fidelity in cooperative cases, like cooperative pulse cases?
Okay, so let me start. Thanks. I'll start with the first question. So I think in the second part about the echo sequences, I went a little bit in more details in these R values. So if essentially you can define many R values, and you have these Euler angles. I mean, this for each pulse there's this alpha, this gamma and alpha angle. And for each you can define an R value. In the case of the Ramsey, I mean, out of the 4. Alpha gamma of the first and alpha gamma of the second pulse. 2 you could ignore, the gamma of the first and alpha of the last. So you are left with 2 angles, and each has a R value, and in general they could be different. What we optimized for is just the overall R value. So basically we have an effective evolution during the first pulse and effective evolution during the second pulse, and we just combine them to one R value. But they didn't need to be the same. However, in the end, when we looked at the pulses, because overall the problem was very symmetric, it turned out we have these pulses with this very special symmetry. And this also resulted in that they have in the end the same R value, but it was not imposed in the optimization. Okay. And the second question was whether we need to do this if we have a single quantum system. So again, the thing is, I mean, if a single quantum system, if you are close to 100% fidelity, or if you have reached 100% fidelity, you don't need to improve anything, of course. However, I mean, the robustness, and I tried to mention this a little bit in the beginning. So the robustness I considered now was really from to the different detunings, in this case, for example, for an ensemble, and to different scaling factors of the pulse amplitude. However, it doesn't have to be an ensemble. I mean, just simply means that doesn't really have to have, I mean, for each of these combinations of detuning and scaling, there doesn't need to be a spin. It's just that for all these different combinations, the sequence will basically perfectly work. So if you do an experiment with a single quantum system, and you can only calibrate the pulses so well, there will always be maybe some detuning, some scaling problem. The pulses are not exactly calibrated as they should be, or maybe they change a little bit over if you repeat the experiment several times. And then but the same robustness then applies here. It also still will be robust if you have then some slow temporal variations, for example, or from day to day, the calibration is not perfect. So you can maybe get the last 0.999 that you need maybe to reach your some error threshold, for example, also using this cohort. At least one should still consider this option or this possibility to push the limit further using this cooperativity.
Okay. Yeah. Thanks.
Fila.
Hello, can you hear me?
Yes, very good.
Wonderful. So first of all, thank you for your talk. It was very interesting and I gained a lot. In the beginning, you were talking about iceberg pulses, and this is maybe a bit more basic question. I think I might have gotten a bit hung up on one thing you said, which was that you start with them before the evolution time, is how you get pre-focus. But how can you start anything before the evolution? Could you maybe explain that a bit more conceptually for me so that I can understand?
So if I understand correctly, I mean, what we consider is we have a certain pulse. So we irradiate some microwave or some radio frequency during a certain period, and then we stop. So then we have a delay, and so conventionally, you think of the pulse. Here all the control happens, then the evolution starts at the end of the pulse. But in this Iceback pulse, is basically what happens is actually the same as the most simple case where you have basically the simplest Iceback pulse is just a rectangular pulse that you always use. Like if you don't do any composite or shaped pulses, you always I mean, the simplest, we don't have delta pulses in our lab, so we don't have infinite power. I mean, the simplest thing we do is have a rectangular pulse. And already during this rectangular pulse, at the end of the rectangular pulse, we do 90-degree pulse. The Bloch vectors are not all along the x-axis for all offsets, because basically, I mean, during this, I mean, the pulse is not infinitely strong, and for certain offsets, you have a certain evolution already during the pulse. Basically, what it means is at the end of the pulse, the phase is not constant to zero. I mean, it's not zero for all offsets, but there's already a linear phase ramp basically over all offsets.
Okay, so this is about the consideration, like which parts you take into consideration of the system. So you consider the system to evolve during your pulse. Is this correct?
There was some echo or some. Did you understand better? I mean, maybe just repeat. So I mean, or basically, I mean, from what I understood. So basically, during the pulse, actually, I'll show you just. Let's see if I can do that. Amit, probably you need to help me. What I would like to do is to show a simple spin jobs example. So how do I get out here? So my programs and yes, just if you go to spin jobs. We need to
yeah. Can you see the spin drops?
Yes.
Okay. So what I have actually is I just actually let me just, so we have a single spin system. Let me look at the parameters. It's no offset. Actually, let's start with the initial state along the z-axis. So basically, here we have our initial Bloch vector along the z-axis, and here I have these preferences. And in the simulations, I can choose between ideal pulses and non-ideal pulses. So if I have an ideal pulse, and I so actually the pulse sequence I have. So let's take a 90-degree pulse around the y-axis, which would bring me to x. No, I don't want to save this. So this is the pulse now, and so actually, if I start and run, do it slower. So we see we bring the maximization goes down to x, and the final state actually is independent of the offset. So and that was in this case I simulated this for the ideal pulse, where basically during the pulse I ignore all the drift terms. So there's no chemical shift or no offset terms which I consider. So of course it's independent of the offset because it's only the pulse that happens. But if I go back to my options and switch on or basically switch off the ideal pulse, now actually what happens is that, and actually I'll just go back. So now I switch off the ideal pulse. Now the chemical shift evolution is taken into account in the during the pulse. And so basically, if I rotate, I still rotate down to the x-axis. But if I look from the top, you see I'm not quite aligned again with still with the x-axis. Actually, if I change the offset, you see a little bit to the left and to the right. And for example, if I change this to not 2 Hertz, but 10 Hertz, I mean, there's a significant angle. And that is basically the chemical shift or the offset evolution already that takes place during the simple rectangular pulse. And in the end, our composite pulses, optimized pulses, I mean, they live that they also use they have this different information about the different offsets. And so, I mean, in this case, it is like this rectangular pulse. It's like, actually, let's go back to the 2 Hertz case, or actually just like this. Go back to 2 Hertz. So in this case, it is like the pulse was ideal, but there was already, at the end of the pulse, there was already some evolution period. So if I would like to simulate, actually to kind of effectively reproduce this, so what I can do is I choose, actually let me go back here. So suppose the pulse was ideal, so I choose actually X magnetization as the beginning, but now I switch off the pulse. Actually, the simplest way is to just go to delay. So I choose a delay, maybe of 1 second. And so what happens now So basically, we can see as the delay goes on, I mean, the delay goes larger, the magnetization now rotates. And if I now go back and forth between the two effective durations, so basically it tells me I get exactly the same result. And you can think of this as if during the pulse already there was some kind of a perfect excitation where everything for all of that was along the x-axis, but during part of the pulse it already has dephased. And in practice, I mean, as it's excited, as spins are going down, they don't go down to the x, but in the end, the phases of the pulse, of the Bloch vectors as a function of the tuning exactly matches in these two cases. Did that kind of answer your question?
Yes, thank you.
Okay, welcome.
Okay, so thank you very much to everyone. Our time is pretty much to end, and we will give you more information about the next QuSCo on air appointment. We are still trying to clarify the attendance, so who will be the next speaker. We have a name, but we have to give a reply, so just check your email in the next days. And for the other people that will have to stay on for the organization of the workshop, I would say that we reconvene at 5 because it has been 2 long hours and I think everyone needs a little break. Okay?
Okay, yes.
Okay. Thanks a lot.
Okay.
Yeah.
Bye to everyone and to the organizer of the committee. In half an hour, we talk again. Bye-bye.
Okay.
Bye.
Bye.
Bye. Thank you. Bye.